All right, I think we can start. Welcome to our second lecture on NV center spin qubits in diamond. During this lecture, I would like to give you a short introduction into quantum processor in diamond. It seems to be the topic decoupled from quantum sensing, our main topic of these lectures related to diamond. But tomorrow we will have an example of operation of the quantum processor that give you quantum advantage in a field of sensing for a very small number of qubits. So don't think it's decoupled. And we will start now with this nice picture from 2007. It's a picture from the review by David Avshalom, where he gave his idea about how diamond quantum microprocessor can look like. What you see here is the photonic crystal made out of diamond with color centers somewhere here in a hot spot. And the core of this device is NV center that you already know quite well from the point of view of photophysics and spin physics. But maybe just a few words about quantum computing, why it motivated so many research in quantum science and transferring this to technology. It's basically use the power of a quantum bit instead of bit, and this quantum bit can be a state of the quantum mechanical system, and difference to a classical bit that it also can be in a superposition state, not only in an eigenstate. And this superposition state and richness of the Hilbert space, including entanglement between qubits, that's what make quantum computing so powerful. And that was realized already some time ago, but it's still difficult to build a quantum processor up to now. And so there are many systems that are now considered to be perspective as materials or as systems for making small and larger scale quantum computing. Essentially, you need that your system fulfills certain criteria that were first formulated by David DiVincenzo. You need to be able to scale arrays of your qubits. You need to be able to prepare them in a well-defined state. Not sure, there's maybe battery problem here with the pointer. So can we change? It stopped working. Yeah, I think it's maybe it's a battery somewhere. Yeah. I can maybe just go ahead. All right. Okay. Oh, it's definitely working. Thanks. So you need to be able to initialize your qubit. Qubit need to have a long enough coherence time to enable entanglement. You need to be able to perform set of gates, including single and 2 qubit gates, and you need to be able to measure qubits. And all these criteria to be fulfilled in one is pretty non-trivial. There are, however, many systems under consideration now. Electron spins, nuclear spins, photons, flux in a superconducting devices, essentially many systems that do have well-defined quantum states and which are scalable. And there are many platforms now really coming to technologies. Today we are going to talk about two of them, namely liquid state NMR, which was one of the first attempts to realize quantum computer, and then solid state nuclear magnetic resonance, and coupling of nuclear spin to electron spins in diamond. We're not going to talk about other systems. Many of you working with them, and they're also very nice and having their own advantages. But we are going to stay today with spin systems, and we are going to discuss how to build quantum computer from spins. Now, NMR quantum computer, or liquid state NMR quantum computer, is a little bit forgotten field, but it was one of the first area where initial quantum operations were realized. In this case, you build quantum computer from a molecule having nuclear spins, and scalar coupling between molecules allow you to realize operation between spins in a molecule. And the dipole-dipole coupling between these spins need to be averaged, and this happens when molecules rotate very quickly. Then you end up with very simple Hamiltonian, allowing you to realize coupling between spins, allowing you to control individual spins in the frequency domain. And some time ago, very initial experiments that had quite an impact in the field have been realized. Look at this: 97 first NMR scheme published, 98 Gruber algorithm, Josa, decoherence-free subspaces, teleportation, Shor algorithm. This was all realized very quickly within a few years. And then you can think, if this would continue, that would be actually a success story. But by this time, about 2001, there was some debate about scalability. Remember, the first criteria of De Vincenzo was that you can make your system larger and larger without significant overhead. And it was shown that for NMR quantum computer, you actually cannot make system large without losing the signal. And this is because of a non-pure state you're working with. Nuclear spins, even under high magnetic fields, are not prepared in a pure state. If this is a spin down and this is a spin up, then in order to reach the purity because of the thermal relaxation in a 20 Tesla field, you would need 40 millikelvin temperature. And it's also still not very pure state in this situation, but at this temperature, which is reachable, molecules are not liquid. Remember, you need that the molecule rotate. So then you, of course, can say, yeah, I keep my sample at room temperature where molecules are in liquid, but then I would need a field of 150,000 Tesla, which is also not feasible. So this is basically the shortcut, the non-pure initial state. And what you try to do in a liquid state NMR, you always try to start with a mixed state, and you try to shuttle around the spins to get some overshoot, which looks like a pure state. Some fraction of your molecules will be in a pure state, but majority of them not. And that's lead to the situation where the size of the sample scales exponentially with the size of your register. So if you want to make 10 qubit quantum processor, you will need 2 to the 10 resources, molecules, to make the same signal accessible. And so the exponential gain in the speed of quantum computer will be compensated at exponential loss in terms of resources used, because you need more and more molecules. So it's not scalable in a sense. But the challenge is not in a scheme itself. The challenge is in the initial state, this pseudo-pure state, thermalized state of nuclear spin. This is a challenge, and it was realized in the very early days. And today we are going to discuss how to build a computer which is similar to NMR, uses many algorithms that were developed for NMR quantum computer, but now use pure states. Right, so this is our design number 1, quantum computer made out of NV centers that are placed in the array. There is a magnetic dipole-dipole interaction between electron spins of NV centers, and there are also nuclear spins around, the nuclear spin that we already have been discussing during the first lecture. Then spins are manipulated using microwave techniques, using these microwave pulses, and they can be read out optically. So the interaction between spins need to be stronger than the coherence processes in order to create high fidelity 2-qubit gates. And each individual node of this register will consist of NV center electron spin and these nuclear spins associated with carbon-13. And in this case, now we are starting to consider them to be a resource. So they actually coupled by the hyperfine interaction to the NV center electron spin, and they are kind of detuned from the environment. Remember this entangling, disentangling events in echo that appeared with larval frequencies. Those were coming from spins that are coherently coupled. Now we want to use them as a part of the register. Not the very far away nuclear spin, but those are located few nanometers from the NV centers. Now you have 1 qubit to be electron spin, a few qubits around, and this small register you have to couple to the next electron spin. And now we are going to go one by one through the elements. Now, nuclear spins, how we can address them? Actually, if they are located very close to NV center, they are starting to be visible directly in the spectrum of the NV center. Instead of the single spin transition at 2.8 gigahertz, you start to split your transition by the hyperfine interaction. And for the first shell nuclear spin, it's 127 megahertz. If you have 2 nuclear spins of this type, you split again, 3 nuclear spins again, and now sort of you can tune your microwave fields to particular transitions or drive them with radio frequency to drive nuclear spins, and that's allow you arbitrary operations in this register. So you have here 1, 2, and 3 qubits register in a very localized manner. This is the first shell very close to NV center located nuclear spins. If you look in a case of 2 nuclei, C13, you can draw now this energy level scheme, and this is again experimentally observed spectrum. You have addressing of each transition here by selecting proper microwave frequencies. This is 1, 2, 3, and 4. And here in this manifold, nuclear spin feels very strong interaction with electron spins, and they can be driven by radio frequency. So you can drive it with RF1 or RF2. This is this transition or this transition here. So there's a full control. And remember, NV center itself can be polarized by light in a very pure state. So there is no this drawback of having a non-polarized system. So there is at least 1 qubit, NV center qubit, that can be cooled to a very low spin temperature. Now you can think about making a control here in the system. You already know how to control NV center electron spins. You can also control nuclear spins by tuning radio frequency and first polarizing it in this particular state by a pi pulse, then rotating nuclear spin, and then bringing the population back into MS=0 manifold of NV center and measuring it optically. So this is a result of experiments similar to that you have seen for electron spin. Now you have a nuclear spin Rabi oscillation. You can also ask yourself, what is the FID, free induction decay time, coherence time for this? Remember, we designed it as a time of decay of phase between 2 pi half pulses. And so this is an experiment where you see that this FID decays in a longer time scale. And this for this particular nuclear spin is not very long, but in a record value for more distant nuclear spin, this FID can be very long, reaching seconds. On this kind of time scale you can operate. It's good if it's seconds coherence time, but it's sometimes not very good if it's weakly coupled because gates are also then slow. Then simplest entangling demonstrations can be done by just applying first a selective pi pulse, preparing this system in very pure initial state. Then you apply the pi half pulse. You create a coherence for one of the nuclear spins, follow it by pi pulse on this nuclear spin manifold. Let's create the phi entangled state. You can also choose another transition for pi pulse, and you will create a psi entangled state. This state acquired a phase differently compared to a single nuclear spin, and that's you can measure. It's a phase accumulation signal and characterize the purity of your entanglement in this case. You can also then measure the density matrix of the system, and you can also go even beyond, taking the electron spin as another spin qubits. In this case, you apply additional pi pulse, and you will get a GHT state or W state, depending on which transitions you apply the pi pulses in your system. So it's very small register, one electron spin, two nuclear spins, strongly coupled, allow you to generate 3 qubit states within a few angstroms location inside of diamond. So this is a very local register. It's allow quite high fidelity operations, but it do have some disadvantage to be in this design not fully scalable unless you couple your system to further electron spin states. Nevertheless, you can, of course, still get to larger number of nuclear spins, and there are very recent and very spectacular demonstration from Team Tamignao group in Delft. So he was able to take nuclear spin cluster located quite far from the NV center electron spin, and by designing a very optimized echo technique, instead of making a single pulse, so tuning echoes to address these nuclear spins, he was able to do a spectroscopy of very distant and coupled between them nuclear spins. And so he was able to address them in a frequency domain. You see the shifts here are in the hertz range. And it's mean that you can detect this very tiny interaction between nuclear spins. And it's now coming to a scale that is similar to liquid state NMR, but in a solid state processor. And this spectral resolution is actually related to long coherence time of electron spin of NV as a parameter. He was also able to realize a different design, more similar to that we discussed before, where you have an electron spin coupled to nuclear spin. And if you want to make a gate between nuclear spins, you have to go over electron spin. So this technique is faster, because if you start to make gates between nuclear spin based on the interaction, those are really slow. And if you want to make gate now faster, you first make a gate between arbitrary nuclear spin and electron spin, and then another gate with another nuclear spin. This kind of a central spin architecture was realized now in 10 qubits processor. And so here you see how you can select nuclear spins in a frequency domain seen by NV center electron spin. And you can also do conditional gates between nuclear spin using interaction between central electron spin. What you essentially do here, you apply selective pulses on your nuclear spins. And depending on the state of the electron spin, nuclear spin have a bit different frequency. And that means that pulses are starting to be either on resonant or off resonant, and they start to rotate the block vector of the nuclear spin differently in a block vector, block sphere. And so you will then come up to the situation where these states are orthogonal and can be distinguished. And this is the basis for the 2-qubit gates, now mediated by the electron spin of NV center. And so with this, you can scale up from 2 to 3 to 4 to 5 up to 10. But the fidelity of operation, and this is a Sett state fidelity, is decreasing when you take larger and larger number of nuclear spins, because they are located more and more far away. And so the precision of these gates is actually decreasing once you start to take a more and more distant nuclear spin into your quantum register. So again, so this scheme allow you to maybe go to even larger number of qubits, no doubt, but it's not going to produce 1,000 or 1,000,000 qubit processor because of this weakness of the interaction and scaling it with a distance. The scalable design I would like to discuss today is actually design that is based on these registers, consisting the electron spin of NV center and nuclear spins, but now connected via stronger dipole-dipole interaction to a next NV center electron spin. Remember, electron spins are 1,000 times stronger spins than nuclei, so 1,000 times larger magnetic moment. So the interaction is 1,000 times larger compared to nuclear spin, electron spin interaction, and that allows the coupling over 10 tens of nanometers. That's still quite a small distance, but it's larger compared to this few angstrom up to a nanometer compared to design that we have discussed before. What are the challenges here? Actually, even at this scale, addressing single qubits optically can be difficult. Actually, creating electron spins with this accuracy is a challenge too. And I would like to discuss now these two issues. But first, how close again can be spins? So you need to have coupling between spins that is stronger than decoherence. For room temperature, coherence time is limited by phonon relaxation, which is about a few milliseconds. And this is your T2 limit. So you need to have coupling on the order of at least 10 kilohertz. And this crossing point tell you that you need to place your spins on the order of 30 nanometers for room temperature operation. So the electron spins need to be as close as 30 nanometers. What techniques can help? We have seen array already during the first lecture. So this array is what's having a distance between nodes to be an order of 10 micron. That's not good enough. It's good to study single NV centers, but you need to bring them much closer. Then there were some techniques developed, like, for example, implanting NV centers through the holes in the IFM tip or through the mask in a PMMA or in a metal, where the size of hole now defines the precision of implanting nitrogen ions. And nitrogen you can then convert to NV center after implantation. So you don't work anymore with some native ingrown NV centers. You try to take ultra pure diamond and you engineer NV center one by one, and you have to get to regime where NV centers start to interact, where they start to get distance below 30 nanometers. Mm-hmm. Yeah, in this case, you would, for example, take one ion and implant, then shift the IFM to next position and implant again. So that's an important question. You mean how producible is to implant? So to implant nitrogen, you can do pretty well, but not every nitrogen get converted to NV, and this is another challenge. I'm not going to discuss this one in much details, but to implant nitrogen, this first one, that can be done reproducibly and even with a very interesting new approach with 100% accuracy that we are going to see. So the, one demonstration was done actually using a very thick mask and very thin or very small hole made out of mica, and so NV centers have been created in arrays with many copies of registers, and because the conversion was not always 100%, you had to go through many of these registers, find two that are coupled, and then study the strengths of the coupling. So that's basically the current status of this research. So the other more advanced way to implant color center deterministically is just to take one nitrogen ion, and it can be done if you have ion trap as a source. And then you have calcium ions that are usually designed to be elements of quantum computer, but that you now use only to cool a nitrogen ion in a trap, and then take this ion and very precisely shift it to the diamond. So this experiment was designed by Jan Mayer and Ferdinand Schmidt-Kallas a time ago, and recently realized. So I just come back and show you a short movie, how it looks like. To shift myself here. Let me see. Ah, yeah, I know. Let's see. Something was frozen now. Ah, yes. So thank you very much. So the ions get first trapped, and you see two sort of them. One can be cooled, and the other is nitrogen ion, which is not cooled, but cooled sympathetically because it has a certain coupling via vibrational modes, and calcium is released, and nitrogen is now accelerated and placed into diamond one by one, and that's very precise method in terms of the straggling, because the trajectory of the ion can be very well controlled. It's very cold ion. There is no thermal motion. And the second point is it is deterministic. So you always know that there was single ion before. And with this, you potentially can create rows or arrays of color centers. We actually tested this approach, and there is an ion trap designed for ion implantation that was built in Mainz by Ferdinand Schmidt-Kallas. And we tried to implant array, but unfortunately, we're only able to implant some isolated spots because not every nitrogen was converted to NV. So we are confident that every time we have implanted nitrogen ion, but many of them remains in form of nitrogen and not in form of NV center. In order to show that it was really implantation events that created these NVs, we have implanted very rare N15 isotope with a nuclear spin to be half. And instead of this triplet we have discussed before, we now have doublet associated with N15. So we know that it's really our implantation that led to creation of these NV centers, but we are still working on improving yield, that every implanted nitrogen now gets converted to NV center. Now, last approach, I would like to discuss how to create pairs or triples of NV centers is the implantation of molecules. So if you take N2 molecule and you implant N2 ion into diamond, the elements of the molecule will stay very close. So yeah, now you don't need this aperture, but you can now create doubles and triples based on this clustered implantation. And that's, you also can scale maybe to molecules having 10 or 20 nitrogen. So we only done experiments so far with N2. And in this case, we have been able to identify out of many spots, those that have two NV centers. And remember, you can do it via G2 function of light, for example. So the G2 function of light contrast give you a number of emitters. You can also look in more details in ODMR spectra. And you can also try to resolve them really optically. For this, you need advanced microscopy technique. Once you have two emitters that are spaced closer than wavelengths of light, then Abbe criterion of resolution in optical microscopy tells that you cannot resolve them anymore. So the resolution limit is typically given by wavelengths of light divided by optic parameter called numerical aperture, but that will not be larger than 1 or so, and refraction index of material. It's about lambda half, but about 300 nanometers for visible light. And very recently, there were some developments in this field, and these developments actually were designed at first to resolve markers in biophysics. It's also a common problem in biology, how to resolve details in the microscopy picture of the cell. But you can also apply this very similar technique to resolve dopants in diamond. So how the technique works, so you can now take an array of clusters of NV centers, and that's a real picture, and you can apply very interesting structured elimination beam, which deplete the excited state, and this beam has zero intensity at the position you are looking on, and it has rising intensity outside. It's a donut shape picture. Now, all emitters that are in all areas except this 0 point in the center will be depleted, and you will start to see only emitters that are at the very, very center, provided that you saturate this effect. So this is now kind of efficiency of depletion, and it will be 0 here, and it will be completely depleted everywhere outside. This technique can be driven in a positive contrast or a negative contrast regime. With two lasers, you can do it as a real image, and with single laser, you can do it as inverted image, but in both cases, you can reach the resolution that scales now as a lambda, which is wavelengths of light, as before, but now divided by some factor characterizing a Rabi frequency of the light. So the more intensity you place, the more efficiently you deplete, this sharper will be this rising point. And this sharpness of this profile of the response on the molecule or of the color center on the intensity profile, the sharpness of this define the resolution of your microscopy. And here's example. If you zoom in this picture, you can see 3 NV centers that are separated by about 200 nanometers, but the resolution power here is on the order of 10 nanometers. And this is one version of this technique. There is another one which is called Palm, where you switch off one of the centers and the other is still bright. And with this controlled switched off and on, you can reach very similar resolutions. The resource you pay, the price you pay is now not the intensity of the laser, but the time. So you have to pay some resources, either intensity of your laser beam or the time you acquire the data, but you can beat the diffraction limit. And that's very essential for many applications, including measuring couplet color centers in diamond. And so this is example of the experiment now on 2 couplet color centers. This is a palm picture, again, super resolution, but using the second approach, you see that the distance is on the order of 20 nanometers, and you see how precise you can locate now your color centers. This is an optical detection. So you can reach resolutions of on the order of a few nanometers. And this is now the spectrum of these 2 color centers. The lines are separated because 2 color centers have different orientation. So you apply a bias field and they fill different Z components. This doublets here, or you think maybe this is a coupling. It's not yet the coupling, it's coupling to nitrogen. So every NV center do have this N15 rare isotope, and this splits the line into 2. This is the same splitting we were using before for this QND measurements, remember? And the coupling between NV center is tiny. It's not visible in this picture. But if you zoom in again and you sweep one or you flip one of the NV centers, you will start to see the shift of the NV center line because the second NV center was flipped. And this shift is now visible here in this picture. You can also do echoes to make decoherence less visible. On one of the NV centers, you can run the Hahn echo. Remember, it refocuses very slow noise. So it's very helpful for the system to get longer phase memory time. And the second NV center can be flipped. And because of this flip, the first spin acquires a phase. And that can be visualized after the Hahn echo. So if you shift this pi pulse on the second spin, you vary the time when you created this phase shift, and then it's acquired. And then you get the oscillation showing the coupling on the order of 50 kilohertz. This is a coupling you can use now for creating a scalable diamond quantum register. This is a very basic element showing you that coupling is visible. You also can convert it to gates exactly with the same time constant. And so the gates are now about 20 microseconds. And you can basically, using this free evolution period and single qubit gates, you can create entanglement in this system with the fidelities on the order of 90%. Not as high as for electron nuclear spin you've seen before, but scalable because the coupling is a long range coupling. And you can also address now your electron spins individually. And so this is now basically an active field of research, how to improve this scheme, how to improve fidelity of the gates, how to improve the readout of this register, how to improve addressing of individual NV center electron spins. Yes. Yeah, it's a so excellent point. So if you store your coherence on the nuclear spins, then you can cycle. And so actually in this situation, nuclear spins were involved here in these gates. So behind it, the coherence on the electron spin will be definitely gone, except for the Sett technique where you potentially can keep it because you keep it in a ground state, because depletion beam actually does not allow the second one to be excited. So potentially the Sett could keep your second qubit alive, but better way to do it is actually to store information first on nuclear spin and then use this Sett on the electron spin, repeating then back. So swapping back to electron spin, measuring, and so on. Like this Q&D measurement we have seen. In the very end, the readout and the writing, it's always need to be done on pure state if you don't do error correction. So if you run your quantum computer, you will have a classical state actually in the beginning and in the end. So even in a most simple way, you could avoid keeping coherences alive, but this is not true for error corrected codes. There you would need in your register coherence to be kept. And so this is more difficult. And for this, you would need nuclear spins. Right. So next point is really going back to initial idea of having a self-assembled molecule as quantum computer, but maybe not quantum computer, but quantum simulator. So what is a quantum simulator? It's not universal quantum computer. It don't do gates. It don't do Shor algorithms. Don't look in a database, but it's designed to model complex quantum systems with certain Hamiltonian by taking another quantum system, which is under good control, and tuning its Hamiltonian to Hamiltonian of unknown device, and then looking at the system under control, you can model a known system. It's very important for designing new materials, especially materials where spin degrees of freedom is playing a role. To model the spin system is a hard task for classical computer. And so the array of spin is the most natural way to model another spin system. And we had idea to build such a device in diamond. An initial design was proposed some time ago by my colleagues, Martin Plenio, Jamin Kai, and Alice Redska. It is a lattice of diamond now, which have this carbon-13 or fluor nuclear spins on the surface or embedded in. And then vCenter is actually reading the state of this nuclear spins. And again, also for this system, you need to be able to initialize, to cool these nuclear spins and read them out. And this in vCenter is a small magnetometer that is doing this job. Now, you also need to model the unknown Hamiltonian. So this is arrays of spins, self-assembled very nicely on a lattice. Look, it's like a graphene, but now on diamond. It's a C13 atoms in C12 diamond. So it's the same chemically identical atoms that have different nuclear spins. It's an array of nuclear spins embedded in magnetic vacuum. They interact, but they are kind of not dissipating it outside. And we also we looked actually how to model unknown Hybridonions with this. You can take your native Hamiltonian and then tilt the magnetic fields. If two spins are tilted by a magic angle, the interaction vanishes. It's a magic angle. And in order to create some kind of a disorder, you need to create field gradients. You need to create some homogeneous field. And with this, you can model arbitrary array of spins in a different lattices for certain orientation of diamond surface, so-called 111. You can model triangular lattice. For 100, it's a square lattice, and all are different and interesting cases. We also have modeled how in vCenter would look and what we will see from this system. So if you change parameters of interaction, the magnetic fields created by these layers of nuclear spins on vCenter will change if you undergo the phase transition. So it's a order parameter that is transferred to the magnetic fields as a function of tuned coupling. And you can see the phase transition in this system. And that's very difficult to simulate on a classical computer. Of course, these results were simulated on a classical computer, but were done for very small numbers of spins. And so if you want to scale it up, it's a very hard task. Now, how to compare it with other simulators? This is very active field. Ultra cold atoms is a leading platform in this case. So they're very cold. It's 3 nanokelvin or lower that you need to reach. Distance between atoms is large, usually in this case. And in our case, this device can operate up to room temperature. And we actually place atom very close, very similar to materials you want to simulate. And for me, maybe important difference is that you start with a native Hamiltonian of interacting spins, and often you need to simulate the Hamiltonians of interacting spins. So you don't model it very artificially. You take it as a native Hamiltonian and you just tune the strengths of parameter of coupling. So that's very attractive. But it's not easy to build, of course. I was discussing before the atomic engineering of materials. C12 diamond, then one single layer of C13 capping with C12. It's controlling assembly of nuclear spin inside with extremely high purity. And that's still a challenging task. But first steps towards it, we have seen. So we basically, together with colleagues from NIMS, National Institute in Japan, created a very thin, about a nanometer layer of C13 capped by 2 C12 layers. And NV centers were introduced just before, and we have seen the coupling between NV center and the layer. So these oscillations here is a coupling showing the flip-flops between NV center located somewhere here and this C12 layer and a very thin array of nuclear spins located above. So this is a work in progress, and there is no yet quantum simulator built in a full flavor of it, but there are efforts in material science to create such a device. Yes. Oh, no, you fabricate it once, and then you will basically tune the magnetic field or the gradient. So basically the tuning the field to be in magic angle allow you to decrease it in a certain direction. Mm-hmm. Okay, and during last a few minutes, I would like to, yes. Oh yes, so it's an important point I need to mention. So the cooling here is done by NV Center itself. It's a NV Center role here. It's actually twofold. One, it's to measure the state, but also another important role, not less important, is to cool these nuclear spins. So actually, you cool your electron spin, then you do flip-flop with nuclear spins. And so nuclear spin is one of them, is oriented, and then you recool your electron spin and repeat it many, many times. So this is, so you don't rely on a thermal polarization. It's again kind of a pure state design, which is not related to major drawback of liquid state NMR. Oh, yeah. Ah, yes. Yeah. I think having NV centers in this ordered array would be another very nice feature, maybe better. But this approach is a bit unique in terms of precision, how precisely you can place your nuclear spin. It's a self-assembly. The lattice give you basically a template. So it would be a very, I mean, it is possible to also create a few NV centers, but it will be not as precise as nuclei find a way on the lattice. So this is basically what is different here. All right. And now, during last few minutes, I would like to highlight a bit different way to scalability. It's a bit similar, however, to this very first slide designed by David Avshalom of the vision of the quantum computer with these cavities where single color centers are sitting and they are connected by some waveguides. So the idea is to create a computer that is connected by photons. And now spins of individual NV or other color centers will be holding qubits, but the connection is not dipole-dipole interaction. Connection between them or gates will be done by basically sending single photons, and then these photons will be interacting with atoms, and you will get interference of photons conditional on the state of the atoms. They can create a phase shift or even take a different path if it's a strong coupling. And this can be now converted to a scalable architecture. So the advantage of this is that you have outstanding connectivity. By changing a classical waveguides, you can connect any of the spins of a large distance, and you are fabrication tolerant. Even if one of the 1,000 of fabrication step happens successfully, you can discard all unwanted qubits that are not working and connect only those that are working. So this is basically another path, but it's a path that requires to have very identical emitters in terms of optical transitions and have a very efficient coupling between photons and spins. So color centers do have this coupling. Remember, spin transition is connected to an optical transition, but how efficient, how strongly, and these photons need to be also coherent in terms of interfering on the detector. And so InVCenter actually is not the best candidates from my point of view, because most of the photons that are emitted, even at low temperature, are in so-called the phonon sideband, which are incoherent. They are good for this spin detection, but they are not good to connect spins via photons. And the other challenge that need to be considered is sensitivity to strain. InVCenter do have a permanent electric dipole moment in the ground state, and it's very sensitive to local electric fields. So if you have diamond with a bit of strain, it's electric fields, and transition frequencies of different color centers can be detuned, and that's another challenge. And we started to look on more symmetric systems for this approach of connecting spins via photons. And one of the candidates is silicon vacancy, but there are also similar germanium vacancy and tin vacancy color centers. This element, silicon, is very similar actually to nitrogen in terms of incorporation, but it's larger. And because it's larger, when you try to place it on a vacancy position, it will not fit very well. And if there is another vacancy nearby, it will shift in the middle between two vacancies. So although it's a silicon vacancy, actually silicon sits between two vacancies. And this is highly symmetric structure with inversion symmetry. And this structure don't have electric, permanent electric dipole moment, and small fluctuations of the electric field will not affect the optical transitions. So those color centers are much more stable in terms of spectral stability. They also couple less to phonons. So it's a comparison here of fluorescence spectrum of InVCenter compared to silicon vacancy. You see InV have very tiny fraction of a zero phonon line, and silicon vacancy center have a strong zero phonon line, and that's another kind of a important parameter for allowing to couple spins to photons. We studied the basically robustness against strain and fluctuations for very long time, over hours. They keep the frequency in optical domain, not affected by any environmental imperfections. If you look on many of them, they actually have absolutely same color. What means here in color? In this picture, I show color in terms of indistinguishability or overlap within homogeneous line width. So if you have two blue spots here, this is two color centers which are absolutely indistinguishable. And there are two groups, red and blue, but all the blues are actually within 100 megahertz on the same optical frequency. And all the reds are grouped in the other area, and this blue will be now indistinguishable. The photons emitted by these blue color centers will start to interfere, and that's what you need to create entanglement over distance. You can check it by sending photons from two different color centers in a beam splitter and measuring correlations. It's very similar to one that we used before for checking it's a single one or not. But now it's two different color centers, and they still provide you a dip, showing that there is a dark part of the interferometer and there is a negative interference in case if your two color centers are indistinguishable. Right. So the drawback of these color centers is a necessity to operate at very low temperatures. Those have also not only spin transition, but also orbital degrees of freedom. And the spin qubit is really isolated only at temperatures where the orbital states are not all populated, but everything relaxes to the lower branch. And this basically means that the whole experiment that we discussed before, that is nice and room temperature, need to be transferred to a dilution refrigerator to cool it to a temperature below 500 millikelvin, where this happens, this depopulation of the upper state. So it's not to initialize the spins. We need this top temperature. Spins can be pumped optically, as we discussed before, but it's to freeze the dynamics of the spins. And in this case, if you do this experiment, and it's sometimes not trivial to run this all at millikelvin, you need to drive spins with microwave, but it's possible. So this is a microwave line. And here you see a single silicon vacancy center, and you can drive its Rabi oscillations as you did before at room temperature, but now in millikelvin with high fidelities. And you can also actually insert them into waveguides and even in resonator. So this is example of collaboration between teams at Loncar Park and Lukin, where they created a high Q photonic crystal cavities, where a single color center was inserted in the maximum of the field, and now reflection of the resonator was modulated by the spin state of this silicon vacancy center. Now, how this resonator looks like, so there's a very thin waveguides with Bragg mirrors formed by these holes. It's very important to etch the holes precisely to get a high Q factor, and it's also very important to have the surface quality of these devices to be good enough to allow high Q factor. So reachable Q factors are on the order of 10,000. It's not very high compared to large cavities. Those can reach Q factor orders of magnitude better. But mode volume in this cavity is very small. And what matter is a Q factor of a mode volume to characterize cooperativity. So mode volume is on the order of lambda cube. And in this situation, you can now, after designing this cavity, implant these color centers, and even implanted one, because of this insensitivity to other defects and fields, behave pretty good, and they can actually be seen now inside of the resonance of the cavity, and they can actually also modulate the transmission of the cavity by changing the spin state. Depending on spin state, you will have either one or the second frequency of the optical transition, and one will be sort of in resonance with the cavity, another is not. And by sending the laser light or later single photons to this integrated device, you can modulate the reflection. And this is a very basic element to create also entanglement between nodes, where you send a single photon and you don't know from which resonator it was reflected. And with this, you can generate entangled state of atoms in a distant resonators. All right, I think I will skip a few slides and go to the very last one and design comparison between these two schemes, and would like to highlight advantages and disadvantages of both. So you have heard about one design that is based on magnetic interaction between color centers. So it's require very close spacing, a few tens of nanometers. And so creation of color centers with this accuracy in addressing is a challenge. But this technique can work even at room temperature. So it's a kind of unique feature of this quantum computer, because usually you need to cool it. But here it can work, you know, in a very user-friendly condition. You don't need a vacuum. That's another point. So it can be a very robust device for operation. Photonic coupling, it's very fabrication tolerant. So you might have very low yield of fabrication of your devices, but you can select the best one. So this is done in conventional semiconductor industries. When you fabricate transistors, you sometimes discard not working one. And so here you can do it in a much higher threshold way. And in this sense, it's very fabrication tolerant technology. But the scheme of generation of gates itself, it's probabilistic. So I need to say it's scalable, but it's not as a kind of a robust or as fast often as deterministic scheme that we have discussed here. And for silicon vacancy centers, it's require millikelvin operations. For other color centers of this type, germanium and tin, it might work also at 4 Kelvin. All right, so I think with this I conclude, and we will continue tomorrow with applications of NV centers in sensing.
So we had enough questions, but we can take 1 or 2 questions now.
So first, thank you. I have a quite general question. So are there defect centers in 2D materials like graphene, which with similar properties than these defects in bulk material, which might be of interest for future research?
Yeah, I think it's a very interesting point, and maybe I repeat in case if it was not translated. So the question is whether there are color centers in 2D materials like boron nitride that have similar properties, and I think they are. And there are even centers that do have optical contrast of magnetic resonance. They're much less explored so far, so much less understood in terms of the spin physics is one point. And the second point is ability to create them is also very essential. And so far, many studies were done on kind of randomly found defects or maybe created by kind of electron radiation. But ability to create them on demand, I think it's very important. But this is very exciting field too.
Yeah, so if you have more questions, then maybe we can discuss later during coffee break or tomorrow, and then we can move on to the next session. Yeah, so let's thank Fedor again.
Okay, so in a few minutes, we will continue with the company flash talk. We have, maybe you can put this on. What is the actual note? Okay. Okay. Try 1, 2, 3. Hello? 1, 2, 3.
Hello? Ah, perfect.
Okay, no, it's turned off. You can put it. Great. So for the first company flash talk, we will have 2 of them, one today and one on Wednesday. We have Christian Knobloch here, who is actually one of VCQ alumni working in ZKW lighting systems, and he will now talk about what's happening there and the latest element. Thanks.
Hello. Yeah, actually, I hope it's okay if I have a minute to prepare a few things. I just thought I'd bring a few things that you not only have the boring company facts, but also see what we are doing. So just a second. One, two, three. Actually, is it okay to plug in here? Mm-hmm. Okay.
So maybe it's also good to know that the Blue Force company, like they will have their stand until tomorrow. So if you want to interact or talk to them, you have today and then tomorrow.
Yeah. So hello. Actually, my colleague joined me, Herr Kamleitner. He's from the HR department. No wonder why. Is there a pointer or something, or should this one? Okay. Yeah, from quantum physics now we switch a little bit to classical physics, but actually it's also somehow familiar to your topic because we are doing things with light. We are trying to form light, and we are trying to sense light as well. We are ZKW. We are a medium-sized company, I would say. Me, myself, my name is Christian Knobloch. I did my PhD also here in Vienna. Oops, it does funny things. Come on. Yeah, in Professor Markus Arndt's group. I did my PhD on molecules. Yeah, quantum physics on molecules. Oops. In my spare time, I kept my interest for places where no one has been before, so I go caving. But during my professional career, I work for ZKW. And at ZKW, we're trying to make innovative headlamps for cars. So we're trying to build premium lighting systems and, of course, the electronics which drive these lighting systems. And now there's also sensors for automotive industry. Yeah, for this job, we say that we need bright minds to create bright lights. So bright minds, we need, of course, always bright minds. That's why we are also here, and that's why it's our pleasure to sponsor all these fresh, motivated physicists. We already have a few bright minds, so worldwide it's about 10,000. Those are in different areas located. So in Wieselburg, where I am, we are about 3,000. So in Wieselburg, there is the headquarters, and of course the normal development site. Yeah. The sites around the world, there are plenty. So from Mexico to Slovakia, the US, Korea, China, yeah, even in India, there's a small sidestep of our company. So there are many places around the world, and in many places we produce headlamps on the one hand, and on the other hand, we're developing those. This is the site where I work, so it's in Wieselburg. I don't know if some of you have heard maybe, so it's where the beer comes from also. And the second most important thing is car headlights. So this is mainly the development, this is the production. Also here is a bit of development. a lot of things to be done. So we're producing headlamps like this one. This is one that is already commercially available. And the headlamp is a very complex thing. And this is why we need a lot of intelligent people, because you see this is a modern headlamp consisting of different things that have to be simulated, that have to be produced, that have to be constructed. And yeah, all these things need a lot of knowledge. So these are some of the headlamps we produced already for some customers like BMW, Porsche, Audi. This is very recently, but also trucks, motorcycles, yeah, rear lamps, everything you can imagine. In the future, you may think, well, when we want to drive autonomously, like everyone says, where is the need of a headlamp? But in the future, we think there is a lot of light around the car and driving the car. So the rear lamp, the exterior displays, will be, of course, a front lamp, but the front lamp will be also combined with sensors, a lot of sensors. So bring a light onto the street and sensing what is going on the street in the same thing. We like to bring e-mobility a little bit further. And of course, we also have an autonomous driving project, so where we study how light and the production of light and the sensing of light in a car enhances autonomous driving and could get that even further. And all this, as a big company, we also have to be aware of the sustainability part, because resources are limited. And so we also have to think about these topics. So this is the project where we think about autonomous driving. So we study this kind of sensor light production thing. Now a little bit more to my thing. So I'm working on HD, so high definition. So why high definition? So the idea is, nowadays, most of the time we drive with low beam. So it's only half of the road illuminated, basically the lower thing, in order not to glare anyone. If you have a more modern lamp like this one, you have already a high beam that is segmented, so you can deglare parts of the road. And of course, the more pixels you have, the finer you can deglare things. So it's beneficial to drive with most of the light. So you drive in high beam all the time during the night. You see a lot, but at the same time, you do not glare anyone on the road. So of course, we're trying to develop this, and it's almost in serious production now. We have developed a so-called DLP. It's very much like this video beamer here, but very much smaller in order to bring it to the car. So with this kind of scheme, you can either do deglaring, or it's called advanced information beam. You can project things on the road. So you can tell the driver, for instance, okay, turn to the left in about 100 meters, or be aware, do not drive so fast. There is a speed limit of a certain kind. How do we do this? We do this with a DMD chip in these kind of modules in the moment. So this is what I'm working on most of the time. So developing this kind of stuff. So we have some kind of illumination, which illuminates the DMD chip. The DMD chip consists of various micromirrors. These kind of micromirrors turn up and down at a certain frequency. And after that, we send this beam through an objective. This objective has to be calculated. I even have one of these here. So in the end, this part up there becomes as small as this. But we have to design this, and so we do a lot of ray tracing and a lot of physics behind this thing. And also, to combine it to the talk before, we have to think about production tolerances. So that's a very important part in industries, and that's a very crucial part also, to think about that, and with a lot of data to have a detailed look on these kind of things. The next generation of these kind of things is not to illuminate a chip and then go out through an objective onto the road, but the next step is to replace the chip by a pixelated light source. So like this one, it's a microstructured LED chip where you have about 10,000 pixels, and each of them you can turn on and off again. We also try to miniaturize headlamps, like in former days, or current status is about this is a light module, we call it, like which you have here in a headlamp. And in future time, we try to get the optics down to a level which is about this. So it's called micro lens array. And the cool thing is you can do this, do any kind of design with these kind of things. I will show you the functionality a little bit later. We also try the obvious path somehow to implement Fresnel technology, to shrink lenses basically. So making one of these lenses as flat as this one. And the technology we are working on in the moment is to implement also the wave structure of the light. So if you have a normal lens like this, you always have color aberration. So different colors meet at different spots. You can do a very expensive correction of this using more lenses. So more lenses that correct for different aberrations in your objective. But for some aberrations, you can also correct with a certain diffractive structure on your lens. And this is the thing we are trying to implement in the moment. So I have one fresh lens with this kind of structure already here. It's hard to see, but there is a kind of rainbow when you watch it. And this should then make the things even easier. And of course, you can do like holograms, fancy stuff with kind of diffraction. And this somehow closes the circle to my PhD project, because there we did diffraction of molecules. Now it's light again. Yeah. If you have some time, I can show you some kind of functionalities. So this is the microlens array, and such a microlens array can, in principle, produce a light pattern like this. And with this light pattern, you see that this is the part where you drive. So this is the central line. Here you declare the other road user, that would be the oncoming traffic. Yeah. And this is possible for high beam and low beam as well. What else do we have? If you're interested, we have also a current headlamp, which we're currently selling to Audi. I have to see if I can make it working. But this is, for instance, daytime running light. So already here you see there is a lot of optics. So you have to couple out the LEDs that you couple in before. You have to couple it out very homogeneously, such that you have a nice appearance. And you can do a lot of fancy stuff. I hope I can. Like this would be again the low beam. This time a little bit brighter than before. And I think, oops, there should be a high beam as well. Yeah, actually this is a very close distance, so you can see the stripes. If you are further away, then you're in the optical far field again, and these stripes overlap much better. Yeah, and these stripes, Thomas, do you know how to, I guess it's, you know how to.
It's quite complicated.
This is low beam. Yeah, this is, for instance, the Corning light that you have seen. So, yeah. Nowadays, I don't know if you have seen this already on the road. Nowadays, those two things are identical. So daytime running light and Corning light are the same, only of one optics. And maybe we managed to declare also someone. Warte mal, ich check links. Ah. Ich glaube, warte mal. Does it work? Does it not work? Yeah, now. So this is basically the functionality we wanted to show you. So there are different pixels illuminating different part of the road, and those can be turned on and turned off depending on if there is traffic coming or not. Yeah. The car does it for you. So no programming needed for these modern headlamps. Okay, so I think my time is over. If there are any questions, I think we're here for several more minutes. With that, I think I can thank you for your attention.
Thank you very much.
Yeah.
If there are any questions, and can answer. If not, yeah. What do you see as one of the future innovations?
I guess so. Maybe it's hard to answer this question because innovation is nothing that you see coming, right? Innovation most of the time is something, yeah, something that disrupts your kind of work process, so that comes. So maybe we talk about more like the foreseeable future. So I was talking about the different fields in the car and the different advantages. So that in closer time, one thing that will be next is some kind of information beam, like communication. So if a car drives autonomously, a pedestrian on the road probably wants to know if it's driving on its own or if there is a real driver. So the car has to communicate somehow to the pedestrian, because if a car stops somewhere and you don't know, can I now cross the road or not? You want to know this. So there will be some kind of communication. So this is a big part in our innovation branch, so to speak, to invent things that help communicating between pedestrian, or between cars and between pedestrians and cars. So this is the foreseeable future. Also is, of course, when we drive autonomously, sensors are a big field. So we're trying to find out how sensors match into making light closely. Like, for instance, it's once you, so in the moment, the feedback loop that you have if you declare someone is that you have a light source. This light source produces some kind of image. This image is then taken by the camera in the car. The camera goes back to the control unit. The control unit tells the light source, and so on and so forth. And to make this feedback loop much smaller, it obviously makes sense to make all the logic in the headlamp. So having a sensor here that watches what happens and gives a direct feedback to the module that makes the light is of course much faster. So this I would say is one of the next steps, definitely, to make this feedback loop much smaller or much shorter. Besides that, of course, yeah, there are different trends in material science. these optics, so we're doing a lot of optics on our own, and there are pros and cons. For instance, we have lenses that are made of glass. Glass is compared to plastics rather heavy. So we're trying to make plastic lenses on the one hand good because they save weight. So when the car has to move afterwards, it saves energy. On the other hand, plastics is something we want to get rid of. So in material science, we are currently also a little bit or more interested or very much interested in materials that are degradable, especially when it comes to optics. It's very interesting topic, very demanding to find something that has optical quality, which is mass producible. Yeah, and these are the topics that will be in the future of certain interest. Yeah, and whatever kind of innovation comes, we hopefully are prepared.
Okay, great. I think with that we are good to go for the first poster session. Thanks for listening in.